Not accepted.
Good morning, welcome everyone. My name is Adam Michalik. I'm a principal engineer at the Dutch Rabobank. And, today I would like to show you how there's nothing plain and simple with plain text. To start with, if you go to the desktop version of Devoxx, you see this, while it should be this. So by the end of this presentation, you will know what happened here, why it happened, how to avoid that, and many, many more interesting things about text and Unicode. So first, imagine that you are fresh out of college and you get on your first job and you're given a task. Figure out how to convert characters to bytes. Sounds easy. You sit down with a piece of paper, a pen, you start writing down the letters that's, you know, ABC all the way down to Z, digits, some punctuation marks. You write down the numbers, goes up until maybe 100, give or take. By the end of the day, or maybe by the end of the week, you're done, you hand it out to your boss. You think, is that enough? Is that okay? Yeah, should be okay. And it is okay. It's 1963. You've just discovered ASCII. You're a scientist living in America. The computers are only used by scientists. And yeah, your context is just America. You only use the English language. You are aware there are other languages, but anyway, you are limited by the 7 bits that the byte has on the computers. So you cannot stuff more than 128 characters into a single byte. That's fine. You have additional requirements. Computers communicate via a teleprinter, which is like a typewriter with a data cable plugged in. So the computer and you yourself has to control that teleprinter while it's printing text. So you reserve 1/4 of your character space for control characters. And that will stay with us for the eternity. That will stay with us for the rest of the days of computers. The first 32 characters are reserved for things that we will never ever use again, like shift out. Now, computers spread across the globe. Some other people in other countries use different languages, and they would like to have a difference between ribs and zebras, or beggars and zebras. This little dot makes a difference. So for instance, in Polish, you need a handful of characters that are specific to the Polish language. If you go to our southern neighbors, there are a few other characters that they need in Czech and Slovak. Luckily, we just got a bit more space within a byte. 128 characters more. You can stuff more regional characters in a byte if you place them nicely. So a fraction will be dedicated to Polish characters, a fraction to Czech and Slovak. You can fit a bit more at least. But how many can you fit? You want to still fit Norwegian, hopefully. Will the whole Greek alphabet fit in? What about Cyrillic? And let's not even mention the Asian languages. And while you do that, while you fill up that space that you have within that single byte, how do you specify that the particular text is in a particular language? Well, you send metadata, of course. So you define encoding for the text, and then the computer understands that if a byte has a value of 230 and the character set is set to Polish, then it's a letter ch. But if the character set is set to Norwegian, then it's e, I believe. And if it's Greek, then it's a zeta. But if you don't have that metadata, what do? You get garbage, or you get what earlier browsers used to do. They analyzed the text and statistically tried to figure out occurrences of those characters beyond the first 128 and compared those statistics to their knowledge base about different languages. So they could figure out that it's probably Polish. That's why we were getting a lot of garbled web pages early in the 90s and 2000s, because there was the analysis was wrong. And nobody really from the people who were setting up their home pages knew what this car set or this meta tag did, so they just copy-pasted from some other page, which was incorrect. Now, if you did that, you were fine when you were presenting a web page in a particular language. But imagine that you want to mix languages. What then? Do you start writing multi-parts HTML pages? Luckily, that didn't happen. But think about a case where you would like to write a book that translates proverbs around the world. It turns out that the same proverb has almost literal translations across the globe. From what I saw, the meaning of the Chinese proverb is exactly the same one as the English one and the Polish one. But you want to write it in their national scripts and maybe also transliteration to the Latin characters. That's not possible if you set the metadata just to one form of encoding. There's just not enough space for all the scripts. To figure out how to solve this problem, we have to understand a few basic concepts. So what really is a character? The concept goes way back thousands of years, right? Before the computers. So now we are trying to port a very old idea into a digital space. And we define a character like this Platonic idea that everybody has in mind, but it's a bit hard to define it. You will see that the definition given here is intentionally vague, but each one of us knows that a small Latin letter A is a small Latin letter A, and it doesn't matter how you write it. And you know that it's different from a capital Latin letter A. So when you apply this idea of a character to a medium, when you print it or display it, use a glyph, which is a picture. Somebody sat and designed that picture for a particular character. So you can see different glyphs for the same lowercase Latin letter A. And the font is a collection of glyphs for some characters. So obviously, we expect that characters A to Z and numbers will be there in most of the fonts, at least. But we know that there are characters that we don't even know about. This is the known unknown. So if a font encounters a character that somebody would like to display, but there is no glyph, in computers, it should display this little square, which incidentally is called a tofu sign, because it's like a little block of white tofu. And when you start applying those typesetting concepts to computers, you define a code space, which is what we did initially. Our code space was, let's say, 100 spaces large, or 101. And we say that each element of that code space is a code point. And now we are encoding characters between the concept of the character to a code point. So it's an assignment between an integer to a character. So when you figure out those basic concepts, you think, okay, I will invent an encoding, a universal encoding. I will call it my Unicode. I just collect all the characters in the world, everything that is written in all the newspapers and all the books, all the symbols, whatever I see in any medium, I will just write it down in some logical way. So Latin characters together, Arabic characters together. Obviously, every script has its own order and has its own set. You add some padding to make them into nice blocks. You assign them the code points sequentially, leave some buffers maybe for future expansion, and you are done. And that's how Unicode happened. It started with 7,000 characters and a bit, 24 scripts in 1991. And then the scientists thought, the number of characters that we need to support is undoubtedly under 2 to the 14th, so 16,000 characters in total. Which means that 16 bits is more than enough to support all the use cases and then some. Well, they improved on that initial estimate by a bit. Last year, Unicode 15.1 has been released, supporting almost 150,000 characters in 161 scripts. Some of them, or maybe even many of them, are scripts that are not live anymore. So, for example, Egyptian hieroglyphs. But still, it is something that you might want to display. So they had their own space in Unicode. And if you check the Java doc of Javalang character, you will see which version of Unicode is supported in JDK. So with Java 22, you get support to the latest Unicode version. And what does it mean that JDK supports a particular Unicode version? Well, it means that as you iterate, for example, through the Unicode space in Java, and you ask, is this code point assigned? Then depending on the version that is available and supported in Java, you will get a different answer. If you ask what kind of character that is, you might get an answer, it's a letter, or it's a symbol, or there are some other parameters to the characters in the Unicode space. So if you are working with Unicode very closely in Java, then upgrading the Java version brings you support for newer Unicode versions too. So now I will read this quote literally from the Unicode spec. Unicode covers all the characters for all the writing systems in the world, modern and ancient. It includes technical symbols, punctuations, and many other characters used in writing text. The Unicode standard is intended to support the needs of all types of users, whether in business or academia, using mainstream and minority scripts. So basically, if you can write it, it should be in Unicode. And the character is this abstract idea. It's not a physical manifestation of a letter. The whole Unicode space is 1.1 million code points, but only 150,000 is used. And if you look at a visual of the Unicode space, it's mostly empty. Unicode is divided in so-called planes. These are the big squares. The planes are subdivided into blocks, and these blocks are assigned, like I said earlier, more or less to scripts. So you'll see in the little corner there, just at the beginning of Unicode, we have our Latin script. So in the big picture, it's not that meaningful. The CJK, which dominates Unicode, is Chinese, Japanese, and Korean characters. And, well, we probably all know that there are thousands and thousands of them. But there are other scripts. A big majority here in the second plane are some ancient scripts, for instance, and minority scripts. The mostly used scripts are in the first plane, which is called the basic multilingual plane. One more thing that is worth observing is that the gray areas there, so a little part, yes, the gray area here and the two planes over here at the end of the space are reserved for private use. So you can do whatever you want in those spaces. You can invent that a particular code point in Unicode is for your purposes, and if you communicate between systems under your control, you can make those systems do whatever you want with those characters. If you want them to display your own face, go ahead, as long as you have a font that actually will display it. But the meaning of a code point in that private space is reserved to the one who uses that. Now at this moment only, we start thinking, how do I use it within a computer? How do I encode the characters to bytes? We have 1.1 million code points in the whole Unicode space. That is a bit under what 3 bytes can handle. But 3 bytes is not a nice number for computers, right? So a nice number is 4. So Unicode says, well, I reserve up to 4 bytes to encode the code points. And I use a Unicode transformation format, a UTF, to transform the code point number, an integer, into some sequence of bytes. And the easiest transformation that you can have is you take the code point value, which in case of an A is 41 hexadecimal, and you just expand it to 4 bytes. That's a lot of zeros, but that's what UTF-32 is. 32 bits, just put in the code point value there and you're done. You transform the code point into bytes. Well, we would like to save up on those zeros, especially that mostly used characters are at the very beginning of the Unicode space. So this is how Unicode started, with saying that it's a fixed width format and the characters are 16 bits wide. Now there was a little twist to it. They knew that they wanted a bigger space, so they thought about how we can use 16-bit characters and still have 32-bit space. So within the first plane, a little part is reserved over here, and they are called surrogates. There's a high surrogate and a low surrogate. They always have to go together. If you want to generate a character or a code point from the further part of the Unicode code space. So there is some bitwise manipulation going on if you have a high and a low surrogate and you get a code point from the further part. Now, most of us use UTF-8. All the web uses UTF-8, and everybody should be using UTF-8, because most of computing works with ASCII characters, so the ones that you can encode in the first 7 bits. And UTF-8 encodes the ASCII code points directly. So you have a 0 at the beginning, and then just the ASCII value after it. But then, even though it's called UTF-8, it doesn't mean that it only uses 8 bits. It's a variable byte count format. So if a character is encoded, that is encoded, is not an ASCII character, then we get a 1 at the beginning of the byte, of the first byte, and then a certain number of ones that say how many bytes after this one should be glued together to calculate the value of the code point. And then there are some still usable bits that you concatenate together, and then you make up the value of the code point. Right? So after the first 7 bits that encode the ASCII code points, you can use 2 bytes to encode the next characters that use up to 11 bits to encode their code point. If that's not enough to encode a character, then you expand to 3 bytes. You get 16 bits of space. And if you want to encode a code point from the very, very far edge of the Unicode code space, then you need all 4 bits. And that is enough to encode the whole Unicode code space. So for comparison, a character from the very beginning, an ASCII character in UTF-8, just 1 byte, UTF-16, 2 bytes with zeros at the beginning, UTF-32, very straightforward. Then something a little bit more distant, a Polish on, 2 bytes, 2 bytes, 4 bytes. A Korean character, still in the basic multilingual plane, but further up. UTF-8 already needs 3 bytes. Since it's still in the first plane of Unicode, you can still use a single, you can still use 2 bytes for UTF-16, and the UTF-32 always 4 bytes. And emojis, they sit already in the second plane of Unicode, so UTF-8, all the encodings need to use 4 bytes, and you can see how the surrogates are used to generate that code point of an emoji. So you can also see how UTF-8 is very efficient in handling of the space. Maybe only if you are dealing with a lot of Chinese, Japanese, or Korean texts, maybe then UTF-16 has an advantage. So there's a most important thing, a takeaway from this presentation. Make the encoding explicit. If you don't, the assumed encoding should be UTF-8, but you know what happens when you assume. Turns out the other side thinks it's UTF-32. But there's also the other most important thing. Be a mean tester. Use the diversity of your team to put in different scripts. When you're Polish, put in Polish characters in the input fields of your system. Put in some Greek, Cyrillic, put in some Chinese characters, put in emojis, and see what happens. Is it stored properly in the database? Does it come up in the on the web page properly, or not? Let's have some fun. Some real coding to show that it works. So the first question. What is the length of this string? Who thinks that the length is a 1? A few people. Who thinks that the length is 2? Nobody. 3? 1 person? 2 people? 4 maybe? A couple more, and the rest just wants to see the answer. Well, the brave people who said that it's 2, was there anyone? Congratulations, it's 2. Why is that? Because when Java started, it was also the beginning of Unicode, and you saw that Unicode says that the characters are 16 bits wide. So the encoding is UTF-16. And internal encoding of strings in Java is UTF-16, or at least until recently, because in the last versions of Java, they do some logic to compact it a little bit. But still, the length API says how many UTF-16 character or words, I should say. So 16-bit chunks make up that string. And how does that exactly work? It is a single code point, but it's a code point, like I said, that has to be encoded with 2 surrogates. So if the length of the string is 2, then it should be possible to take a substring from 0 to 1, right? So let's see what happens when we do that. A question mark. A question mark is displayed when a character cannot be displayed. So we have 2 surrogates that make up this, this code point. And now we took a substring which separated the high surrogate, but a high surrogate cannot exist by itself. You cannot display it, it's an error. So that's what you get. You get a question mark character. And if we print the cars of this string, which gives us actually the surrogates, these are the 2. A car, a character, is the UTF-16 word that makes up a string. So the 0th car of that poo emoji is just the high surrogate. Now, you probably know that big companies, Facebook, Google, and many that try to imitate them, they employ HackerRank or similar platforms to test their candidates. And they give tasks like reverse a list or reverse a string, maybe. So how do you reverse a string? You iterate over characters and you put them, accumulate them in another list or array or whatnot in reverse order, and then you make up a string out of that. What if a string is something else than just ASCII characters, which would be probably everybody's default? Well, the reverse gets garbled up. Incidentally, we get this toilet seat in there. But why is that? So the initial code points of the input string are these 2. The characters that make them up are these 4. So high surrogate, low surrogate, high surrogate, low surrogate. You can see that the high surrogates are both the same. When you start writing the characters in reverse, you end up with low, high, low, high. And only in the middle you get a proper order, high, low surrogate. So that can be understood as a code point and displayed as an emoji. And the other 2 are broken. Of course, the question is, how do we fix it? Very easily. String builder reverse. All the knowledge is there. String builder knows how Unicode works and how it shouldn't separate the surrogates, and it just the reversion for you. I wonder if that question, if that answer would be satisfactory on an interview. Let's quickly see how the encoding works for real. So we are encoding again a slightly more complicated string. And you can see in different UTF formats, it is encoded differently. One quirk for UTF-16 and for UTF-32, you can write the bytes in different order. So you have little endian and big endian. You can see that the order is reversed in each word. So the 3D goes here and A9 goes here, and in the UTF-32 the whole four bytes are reversed in order. for UTF-16, there is no default endianness. So you prefix it with a byte order mark. FEFF means it's big endian, and FFFE is little endian. So again, if somebody asks, so how many bytes do I need to encode a string? The answer is, it depends. And if somebody asks, and if it's UTF-16, well, it still depends. The last encoding is the default platform encoding, which is used if you, in some APIs, when you don't pass the encoding explicitly. Most often it's UTF-8, but sometimes it's not, so don't use the APIs without an explicit encoding. Now, I said that the publisher and the consumer of an API have to explicitly agree on the encoding. What happens if they don't? Here's the encoding of the publisher and the encoding of the consumer. And this, on the right side, is what the consumer decodes. So we are always encoding this string. And here are a few examples for Polish characters, Korean characters, emojis. You see, only if the encodings match, you get what you were intended to have. Otherwise, it just becomes garbage. Hopefully, if you store it and then you read it, then the encoding is reversed, but don't count on it. Okay, another question. We have two letters, U umlaut. Are they equal? Who thinks they are equal? It wouldn't be here if they were equal, right? Of course they are not equal, but why? It's a trap, yes. And it's a trap that you should use to test your input, or somebody else's input, it's even better. Like, dude, I wrote an U umlaut and your system crashed. So the first U umlaut is just a single code point, DC. But the second U umlaut is made up of two code points. It's the letter U, and it's something. It's something added to that U. It's a free-floating umlaut. So you have diacritical marks that are separate entities on their own, and you can attach them to letters. And you can attach more and more and more different diacritics to the same letter. But how can you compare the two characters which semantically should be the same? It's just an U umlaut. Well, there are normalizers in JDK. I will quickly show the helper method here. So there's a class normalizer that has several form enums, and you can use those normalizing forms to normalize your strings. There are 4 flavors to it. One is called canonical decomposition, canonical composition. So you can see decomposition rather splits a code point apart. So it's split it into a U and a free-floating umlaut, and the composition rather composed it into a single code point if it's only available. There's also compatibility, decomposition and composition, which incidentally give the same results this time, but not for long. So look at this one. A list of 3 words: affirm, affix, Africa. They are written in order, in lexicographical order, right? So when we sort them, they should be in the same order, right? Surprisingly, they are not, and you probably can see that this affirm looks a little weird. So this FFI is called a ligature, and it's used in typesetting to display some characters more nicely when they are together. So it turns out that if F and I are next to each other, they don't look nice. They just have weird space. It stands out when you are reading text. So in typesetting, you have a separate glyph to display those two characters in one go, and then they are a little bit closer together, less gap, and sometimes they are even connected, like here. You can see the F is connected to the other F and to the I. But when you get an input like this, it's a totally different code point, and if you are sorting text that contains such a code point, it is in a totally different place in the Unicode code space. What do? Well, we just saw the normalization technique. We can compare the ligature and the split value. So a ligature is a code point in itself, and these are just letters, FFI. If you do the canonical decomposition and composition, nothing happens. But the compatibility version, it splits apart the ligature the way that you would like. So if you want to have proper sorting of that list, you have to normalize with canonical decomposition, and then you get the order that you wanted, as if the ligature was literally FFI. Now, to go to the pain points from the second slide of this presentation, how the title of the presentation got messed up. This is what I used. I used Zalgo-text, which is a funny name for this kind of evil, menacing kind of text that contains many, many stacked up diacritical marks. And if you count how many code points we have here, it's a mere 54. And it goes all the way to infinity. So suppose you are not interested in all that garbage. What can you do? Apache Commons to the rescue. String utils, strip accents. You get a nice, clean Zalgo text with just 10 characters and 10 code points. Let's have some fun with emojis now. So there's a boy meets a girl. They are on equal rights, so they can reverse their roles. Let's see what happens there. After some time, they get a child, or maybe two, a boy and a girl. How does that work? Well, look at that. A boy, a single code point. A boy and a girl. Is this love or is it something else? It's a zero width joiner. That's what keeps them together. That is what makes this glyph be a single glyph and not a separate man and a separate woman. But you can reverse this string and you can see that you literally get a different glyph with the woman in the first place. So there's another glyph, and all these glyphs are defined in emoji specification that you literally have to connect the code point of a man and a code point of a woman and a code point of a boy and then of a girl with zero width joiners to get those emoji glyphs. So all platforms that want to support a certain version of emoji specification, and yes, there is emoji specification, they can see that, oh, emoji version 2.0 introduces this zero width joiner sequence called man, woman, boy, girl, and it is made up of those character points concatenated with the zero width joiner. And then different platforms display this family in different ways, but the idea is the same. And you can see that, well, just as written here, it's 7 code points, but a single glyph. Another example. A teacher. A teacher consists of 4 code points. What are they? Why do we need so many? So in fact, this single emoji is a woman with a skin color modifier, dark skin, I think it's called, in a school. What do you have when you put a woman in a school? You get a teacher. Same applies to a man. And you can recognize this skin color modifiers from different apps that let you set your skin color modifier for the thumbs up, thumbs down, and all the other emojis. So these can be attached to different emojis to modify the skin color. Now, at the very beginning, we had the question about the length. And it didn't make sense to count the characters. It made some sense to count the code points, but still, if you display a family like this, most sane people would say it's 1, right? If you display the teacher, it's also 1. These are 2. The length is 2. And this looks like 10-ish. So how do we get a result that is compatible with our very basic cognitive function of looking and seeing just one thing? There is a big and complex API for that. That yields correct results. So answer is 1, 1, 2 separate things, 10 separate things. The things are called grapheme clusters. So grapheme is something that you display, and a grapheme cluster is many of those things that make up a single thing. After those examples, you more or less get the idea that the family is a single grapheme cluster, while the family and the teacher are 2 separate grapheme clusters. And if you go that deep into counting the length of a string, the API is there in JDK. So in Java text, there are break iterators that allow you to iterate over different sections of text. You can iterate over words, sentences, and you can iterate over characters. This way, like you see on the screen, you can count the length of a string, count the characters in terms of grapheme clusters in the string. If you are on a JDK that does not support the newest Unicode version, but you would still want support for this API, there is an SPI in JDK for that, so a service provider interface. You can drop in a jar that is generated or created by the Unicode consortium, add some parameters to the JVM, and that SPI will be used. So you can that way upgrade your Unicode version without upgrading your JDK. And that way you can get reliable counting of characters in a string. Now, the next time that there is user input and you have a length limitation on a database or length limitation in the UI, try testing that with this kind of input and see what results you get. And you at least get the same results all across the system. If you get UI validation, backend validation, database validation, do they yield the same results? I'm 99% sure that they do not. That's the end, and we have time for questions if there are any. What a mess. We did it to ourselves. We could just use the English script, right, everybody? Sorry, I think I have to come over. I didn't hear a part of it at least. Can you use those special texts as variable names? Yes, you can. The Java source code is UTF-8 encoded, and you can put well, any UTF-8 character as a variable name. So I could have a var umlaut. What is that? Well, it is here umlaut, right? But let's see if I can get a var family. Somebody doesn't like that too much. But maybe... Hey, that's weird. What about this? Maybe it's just the IntelliJ. So you never know. I would have to compile from the command line. In principle, I don't remember reading anything about any parts of Unicode to be excluded from being a proper identifiers. So knock yourself out. Create a class with a family icon, and then all the methods are other emojis. I'm gonna test that after the presentation. The whole family. Yeah, let's see what happens. So will the children rule over the parents? Nice one. Well, I'm gonna just delete that. Hopefully this works. Okay. It starts falling apart because yeah, it does. When children rule over the parents. The emoji specification says this is the zero width joiner sequence to display man, woman, boy, girl. And they define all the permutations of that, but not this one. So I guess because it goes from the end, we get the boy connected to a girl, but there is no glyph for that. Then we get a zero width joiner, but it doesn't really mean anything. And then we get the woman and the man. So this is understood by the font, and it is displayed together. Any other questions? Yes. To get space estimates. Yeah, the question was, on the database? How do you make space estimates if you can get input like that? Well, most of the time, probably you can assume that it will be ASCII, or it will be mostly ASCII, so it will be 1 byte per character. If you are dealing with emojis, well, just count times 4. I'm not particularly sure when you use a varchar character, a varchar type, and you define the encoding to be UTF-8, how much space is reserved or whatnot. But as usual, you set something up, you put it live, and then you adjust. Thank you very much. If you have more questions, come on over. I'm happy to discuss everything.